Hello. So today we'll continue with our basically reviewing of the math that is needed for this course. So last time we ended with the topic of sets of measure zero, and the idea was that basically there is something called the Lebesgue measure, which is a generalization of the concept of length in one dimension, area in two dimensions, volume in three dimensions, and so forth. And that basically there are sets that has a measure zero. And the definition basically is that those are the sets in one dimension. You can cover them by intervals, and then if you find basically the measure of those intervals or an upper bound on the measure of those intervals, you get something that can be made arbitrarily small. In that case, we say that the set of is measure zero. Okay. Okay. What's the question?
So, just a quick question. In covering the elements, are you covering the whole set, or you are covering one element?
Yes. So if you are studying a set, let's call it set A, then it must be a subset of the union of intervals. So you must cover everything here by the union of intervals.
So in the last lecture, when you were writing like xj or something, you were referring to the whole set.
Basically, yeah. So basically, for xj, and this is true for every j. So when we did the proof, xj was covered by basically an interval that goes from xj minus epsilon over something to xj plus epsilon over something. So this is not the only interval, of course. Basically, your cover is the union of all intervals, and with each x there is an associated interval, so that you are sure that the set x1, x2, x3, and so forth, this is a subset of the union of intervals. And then we studied the union of intervals, and we discovered that its measure or length can be upper bounded by epsilon, and epsilon is an arbitrary positive number. So basically this means that our original set, which is this set here, composed of a countably infinite collection of points, is of measure zero. Okay. Now this is true. So keep it in mind that all finite and countably infinite subsets of R are of measure zero. Okay. So any set, for example, the set of rational numbers. Okay. The set of rational numbers, its quote-unquote length or its Lebesgue measure is exactly equal to zero because it is a countably infinite set. Any set that is finite or countably infinite is of measure zero. Now, if your set is uncountably infinite, then basically you have, it may be of measure zero or not. So yes, there are uncountably infinite sets that basically have a measure of zero, like something called the Cantor set, okay? And there are so many other sets. So to have a strictly positive measure, your set should be basically okay. So any question or something? No? Okay. So let's go back. Okay. So if your set is to have a positive measure, then it needs to be uncountably infinite. But there are some uncountably infinite sets that basically have a measure of zero. Now, what is this business of measure zero? I mean, what is its relevance? Okay. So the trick here, or the idea, is this concept. So if you do not know it from your previous lives, so here it is: AE, almost everywhere. Okay. So so we say that some function has a certain property almost everywhere. So for example, that the function is positive almost everywhere, AE. So it means that it is positive on the whole real axis, perhaps except at a set that has a measure zero. Okay, so this is, the meaning that some function has a property that is, that is almost everywhere. So almost everywhere, it's not everywhere, right? So it is not for all real numbers, but you can basically violate the property, but you do so on a set of measure 0. Okay, so let's see. Let's take, because this function we'll use it several times. So the indicator function. So this is a function, indicator function TQ, and so this is the set of rational numbers. So what is this function? So this function is 1. It is equal to 1 if basically if t is rational. Okay, if it's equal to 1 if t is rational, and it is equal to 0 if t is irrational. Okay, so this is the function, and again it will play some role with us in this course. So it is a function that is weird. Actually, it is discontinuous everywhere, and it is a function that is 1 whenever its argument t is a rational number, 0 otherwise. Okay. So, for example, from this function is, you can write something like this, that indicator t rational is equal to 0. It is equal to 0, okay? Almost everywhere. Why is this true? Because the function is 0 at every point on the real axis, except when we are talking about the rational numbers. The rational numbers are huge. They are dense. You find them everywhere on the real line. However, they are countably infinite, and so their measure is equal to 0. So this statement here is true. The indicator function is equal to 0 almost everywhere, AE. So it means that, yes, these two sides, the left-hand side and the right-hand side, are indeed equal, but there are violations. What are the violations? The violations happen for the values of t that are rational. So violations happen over the set of rational numbers where this indicator function is equal to 1. Well, the set of rational numbers is a set of measure 0 because all countably infinite sets are of measure 0. So this statement here will be true. If I say that a function is positive almost everywhere, then I mean that it is positive, but maybe it is 0 or negative. But if it is 0 and negative, this should happen on a set that is of measure 0. Okay, so this is the concept of almost everywhere and equality almost everywhere. Okay, now if two functions are almost everywhere, okay, then, on some subset of R, then their integrals are equal. Okay, so this is a property, and like a deep understanding of this property requires an understanding of Lebesgue integrals, but actually we will take this for granted, and basically the integrals that you will do will also be Riemann integrals. So you will not have to do Lebesgue integrals, okay? But again, if two functions are equal almost everywhere, then basically their integrals are the same. So it seems like integration is insensitive to basically differences between functions, so long as these differences are on a set of measure 0. So an application for this, let's assume that you try to integrate this function from 0 to 1. Again, this function which is 1 whenever t is a rational number, and 0 if t is an irrational number. Okay, so here is this function. Now, the Riemann integral of this function if you want to define a Riemann integration for it, the Riemann integral is not defined. So this function is not integrable if we do, conventional integration, the Riemann integration. But it is integrable if we use Lebesgue integration. Okay, so it is integrable, and actually this integration, it has a value. What is the value of this integration? It is 0. Why it is 0? Because this integration is exactly equal to the integral of 0 dt from 0 to 1. So it is equal to 0. Why is this the case? These two things are not the same. Definitely a function that is 0, exactly 0 from 0 to 1 on the interval from 0 to 1 is different from a function that takes the value 1 whenever its argument is a rational number. However, these two functions, they are equal. Not equal in the sense they are equal everywhere, but they are equal almost everywhere. Because basically they differ on the set of rational numbers, right? So basically these two functions, they are different whenever t is rational, but the set of rational numbers is countably infinite, and any countably infinite set is of measure 0. So if two functions differ on a set of measure 0, then basically they are equal almost everywhere, and their integrals are basically the same. Okay, so integrals are blind to differences happening on sets of measure 0. And this is what we need basically for things like the Fourier analysis and so on. Okay? So almost everywhere is a concept that will again be useful for us later in the course. Now, continuous functions. Basically functions, in signals and systems, basically signals are functions. Okay, so it's like we call things signals. They are exactly functions. And if a function is continuous, it has a number of properties, okay, that you studied, maybe actually in high school or something, when you studied calculus or in college. Basically, these properties are very important. So this is like sort of a reminder, without like going into proofs. Maybe I will prove just one of them and so on. So a continuous function defined on a closed bounded interval. So if you have an interval here from A to B, okay, and basically you have a continuous function defined over interval, then this continuous function is guaranteed to be bounded. So if you have a continuous function, again on an interval, the interval should be closed and finite. Okay, so it goes from some A to some B, it's finite. Then in that case, the function is bounded. And what is the meaning of a bounded function? The bounded function means that the magnitude of the function, or its absolute value, is basically less than or equal to some number, and this number is finite number. So it is strictly less than infinity. Okay, so again, functions that are continuous on a closed and finite interval, those functions are bounded. Okay, so here is an application. So if you are integrating the absolute value of x of t, and it is a continuous function on the interval from -L to L, then it is upper bounded. So basically its magnitude is less than or equal to some number that is finite. So you can upper bound this integral here by replacing the magnitude of the function by some finite positive number. Okay, and so this integral here is upper bounded by m multiplied by the integration of 1 from -L to L, which gives you 2L. Okay, so basically, if you have a continuous function and because it is bounded, if you integrate it over a bounded interval, you get a finite number. Okay. Now, if there is a continuous function, again defined on a closed and bounded interval, then the function achieves its maximum and its minimum. It achieves its maximum and its minimum, but the interval should be closed and bounded. Okay, so there is, those intervals are a special class of something. I'm sure some of you already know this. Those are called compact sets. Okay. So if you define a continuous function on a compact set, then it achieves its maximum and minimum, right? If you have a continuous function that is not defined on a compact set, then this may not be true. So let me give you an example. So let's assume that you have a simple continuous function, x of t, that is equal to t. And let's basically study this function on the open interval 0 and 1. Okay, so this is the function, this is t, and 0 is not part of the domain, 1 is not part of the domain, so this function, so if this is 1, this function goes like this. Okay, so this is our function. Okay, so here we are violating, so basically the interval here is not, I mean the interval should be closed and bounded, but it's open here. So basically what is the maximum of this function? So what is the maximum of x of the function is t, so what is the maximum of t when t is in the open interval from 0 to 1? And what is the minimum of t as t is in the open interval from 0 to 1? What is the maximum and what is the minimum? Any ideas?
It doesn't have critical points.
Exactly. So basically this maximum does not exist. It does not exist because you can get very close to 1, but you can never achieve 1, right? Because how do you achieve 1? You need t to be equal to 1, but you are not allowed to make t equal to 1 because this function is defined on an open interval from 0 to 1. So the maximum here, it does not exist, doesn't exist. Okay, and the minimum also doesn't exist because you say the minimum is 0. No, it is not 0. 0 is called the infimum. But it is not a minimum because basically it is not achievable. What is the value of t here in this basically set that will give you 0? No one, no value, because you say 0. 0 is not included in this interval. So you can make the function x of t equal t, you can make it as close to 0 as you wish, but it will never attain the value 0. So the minimum also does not exist. Okay, so for a continuous function, to basically achieve its maximum and minimum values, it should be defined on an interval that is compact. And compact is basically these two properties. Basically, the set should be bounded and it should be closed. Okay? Now, this property is nice, and actually we will use it. Now, suppose that you have a continuous function and you are sure that the function is strictly positive at some t bar. You are sure that it is positive, okay? Then it must be the case, that there is an interval about t bar on which the function is strictly positive, right? So a function, you know, so there is this t bar, and you know that the function at t bar is strictly, it's some positive number. If the function is continuous, then not only is it positive on t bar, there will be a neighborhood for t bar on which the function is strictly positive. And the intuition behind this is that continuous functions do not jump. So if you start at a point and you are strictly positive at a point, then to go to negative values, then you cannot do so except by moving smoothly, you know. So to basically to go to 0 or to go to a negative number, and since the function is continuous, you just have to go to 0 or go to negative numbers. You cannot jump because this is a continuous function. And the same is true if some continuous function is negative at t hat, then basically there exists an interval about t hat on which the function is strictly negative. Okay, so how we can prove that if there is a point at which the function is positive, then it is positive in a neighborhood of that basically point. So x of t is continuous at t bar. Okay, so that's the definition of continuity. What does it mean for a function to be continuous? So the epsilon delta definition of continuity tells you that the function is continuous if for every epsilon that is greater than 0, there exists a delta, a positive delta, such that for every t that is within delta from t bar. So here we are talking about the neighborhood of t bar that has a width of delta. So for every t that is within delta from t bar, we have the difference between x of t and x of t bar is less than epsilon. Okay, so that's the definition for a for a continuous function at a point t bar. Okay, so so basically, if the function is continuous at t bar, then again, if t is close enough to t bar, then basically the absolute value of x of t minus x of t bar, or the magnitude, is less than epsilon. And we know that the absolute value is greater than or equal to x of t bar minus x of t. Okay, so because the absolute value of alpha is greater than or equal to alpha, and the absolute value of alpha is greater than or equal to minus alpha. Okay, so we know this. So the absolute value of x of t minus x of t bar is greater than or equal to x of t bar minus x of t. Okay, so what can we learn from here? So move this x of t to the other side. So x of t is greater than or equal to x of t bar minus epsilon. So again, if t is very close to t bar, if t is within delta from t bar, then x of t is greater than or equal to x of t bar minus epsilon. Now, by definition of continuity, this should be true for any positive epsilon. So basically, you can choose epsilon. It's true for any positive epsilon. You can choose epsilon to be equal to x of t bar over 2. Right, because the function is strictly positive at t bar, so x of t bar is a positive number, x of t bar over 2 is a positive number. So this means that x of t greater than x of t is greater than x of t bar minus x of t bar over 2, so this is equal to x of t bar over 2. So x of t, so in a closed neighborhood of t bar, it will always be the case that x of t is greater than x of t bar over 2. And x of t bar is a positive number, divided by 2 is a positive number, so this is a strictly positive. And this is what we need to prove, that basically if a continuous function is positive at a point, then there is a neighborhood of this point, there is an interval about this point on which the function will remain strictly positive. And if the function is strictly negative at a point, there will be an interval about this point on which the function is strictly negative. Okay. Now, interchanging the order of operations does not necessarily yield the same results. Okay, so you can search for many counter examples in which, like, if you do a double integral, integrating first with respect to x, then with respect to y, you will get a different result than if you integrate first with respect to y, then with respect to x. If you have two infinite sums, again, you do the sum first with respect to I, then j, you may get a result that is different than if you do with respect to j, then I. And the same story if you are basically doing an integral and an infinite sum. So basically, interchanging the order of operations, is not always valid, in the sense that you may not get the exact same result. Okay, so what are cases in which basically the interchange will not affect the result? So one of them is basically if you are dealing with a function, a function that is real valued and non-negative. So basically, if your function is real valued and non-negative, then you can do the operations in any order of your choice, and you will get exact, the same exact result. So this is Tonelli's theorem. Okay, so if g of mn, or this function h of uv, if it is real valued and non-negative, then without hesitation, you can interchange basically the order of summation, infinite summation, or integration, and you are guaranteed to get the exact same result. So we have this equality is guaranteed to be true, and this equality is guaranteed to be true. Okay? Now, in signals and systems, mostly we will deal with functions and signals that are complex valued. So complex valued, so basically, so sometimes actually we'll deal with functions that are real valued and non-negative, but there are cases. In the case of Tonelli here, these quantities, that's a good question. These quantities are defined. These quantities are defined. If you sum, for example, if you are summing non-negative, basically functions like this, summation gm from 1 to infinity, n from 1 to infinity, g of m and mn is greater than or equal to 0, then you have just two possibilities. Either this summation is a finite number, a finite non-negative number, or this summation is plus infinity, okay? And so the reason is that the partial sums, so basically this is an infinite sum. If you take the partial sum, so basically this is, again, this is true for every m and n. Yeah, this is true for every m and n. Okay, and this is true for every, for every value of u and v in the domain of integration. So this is for every u and v, in the domain of integration. Yes, of integration. So if this is always non-negative and this is always non-negative, then again, the integrals and the sums are well defined. They are well defined because you either get a result that is a finite non-negative number or plus infinity. Okay, and so both are well defined. You will never be in a situation. In which the sum does not exist. There are oscillations and some stuff like this. Okay, and the reason again is that if you have something that is non-negative, so if you take n from 1 to n, so those are the partial sums of something that is non-negative. If you increase n, what will happen? If you increase the upper bound, because the terms are non-negative, then basically what the summation remains the same, or it increases because you are adding terms that are non-negative. So basically the sequence of partial sums, this sequence is monotonic. And because it is monotonic, then basically you have one of two possibilities. You either go to infinity plus infinity, or if the sequence is bounded, then you go to a limit, a finite limit. Okay, but never is, there is no case in which, like, for example, the sum may not be defined. Now, this is not true if you are summing something general, like a complex valued function or a function that is real valued but can be positive and negative. But this is also a case of importance. So what is the story here? Now, if you want to swap the order of integration, and you are integrating a function that, generally speaking, is a complex valued function. So now, yes, in this case, you may actually argue that maybe the integral is not even defined. Yes, that's true. But here is a condition, that if it's satisfied, then the swapping, actually you get an integral that is defined, and for you can do the integration in any order of your choice. So this is the condition. So this is called Fubini. So this here, which tells you, okay, so you want to basically check that this is equal to that. Okay, then what you do is that you go to the magnitude. So you take the magnitude of this thing. Okay, so the magnitude is the square root of the real part of HUV squared plus the imaginary part of HUV squared. So you take the magnitude, and then when you take the magnitude, you try to do the double integral of the magnitude. If you get a result that is finite, then basically these two guys are defined, are well defined, and they are equal. So here, regardless of the order of integration, you will get the exact same finite result. But here, it's a bit more complicated than Tonelli. Tonelli is it's basically, you have equality. And by the way, the equality extends to the case of positive infinity. So if this is real valued and non-negative, and this thing here is plus infinity, if you go and compute this other thing, you are guaranteed also to get plus infinity. Now here things are a bit different, and you will need, if you want to interchange, well, you will have to check basically a sufficient condition that validates the interchange of the order of operations is to apply the double integral or the double infinite sum or basically the infinite sum integral. You apply to the magnitude. You get something that is finite, then you can interchange. And in this course, we will also encounter cases in which we need to justify the interchange of limit and integration, or limit and infinite sum. So when is this true? What is a sufficient condition for this to be true? So here again, let's basically read what the left-hand side is saying. The left-hand side is saying that you have this function that depends on t and epsilon. T is basically the dummy variable of integration, and epsilon is like a parameter. So when you do this integration, you do it fixing epsilon, and you do the integration with respect to t, and when you are done, you end up with a function in epsilon. Then you take the limit of the function as epsilon goes to a. Now the right-hand side, basically the order of operations is as follows. Now here you go first and you fix a t. For any fixed t, you basically compute the limit of epsilon t as epsilon goes to a. And once you are done, you will get a function that depends on t. This is now your integrand, and so you integrate it. Now, generally speaking, if you do this and you do that, you may get different results. So what is sufficient condition that ensures that basically these two quantities are the same? So basically the idea is, and this is the dominated convergence theorem, is that if you take this integrand, specifically if you take its magnitude, so you can take its magnitude, and you can upper bound the magnitude. You upper bound the magnitude by a non-negative function that depends only on the dummy variable of integration. So basically the upper bound here is this non-negative function. It does not depend, it's true. This upper bound is true basically regardless of epsilon. The upper bound does not include epsilon. If you can do this, and basically the integral of x of t is a finite number. So basically x of t is integrable. So you can obtain this upper bounding step with an upper bound that does not depend on the variable with respect to which you are taking the limit. And if also the integral of x of t dt is a finite number, then basically this equality holds. Okay? Let's do an example. Suppose that you have a function eta of t whose magnitude basically is integrable. So the integration of the magnitude is a finite number. Now, assume that you are interested in this limit. So you have the limit of epsilon goes to 0 of the integral of eta of t e to the minus epsilon t dt, and I here is basically the square root of minus 1. So here again, you know that some people like use a j. Here in this course, we will use I. I is the square root of minus 1. So is it true that we can actually take the limit and move it inside the integral? Can we do the limit first? So basically, if you can apply the dominated convergence theorem, then this is one way for justifying taking the limit inside the integration, which means that you interchange the order. You do the limit first, and then you do the integration. So this is the function. So the dominated convergence theorem tells you first go to this function, take its magnitude. And the magnitude of the product of two complex quantities is simply the product of magnitudes. Okay. Now, upper bound the magnitude by something that does not depend except on the dummy variable of integration. So you should not depend on, basically the upper bound should not depend on the variable involved in the limit. So basically this function, its magnitude is exactly equal to the magnitude of eta of t, and this depends only on t, multiplied by the magnitude of e to the I epsilon t. This depends on epsilon and t. But this is something that is nice. This is a complex number that lives on the unit circle. So basically the magnitude of this number is exactly equal to 1. So basically the magnitude in our case is magnitude eta of t, which is less than or equal to the magnitude of eta of t. So you can take the magnitude of, this magnitude and upper bound it by something, okay, that does not depend on epsilon. Moreover, by, this is in the problem statement, moreover, this upper bound is integrable in the sense that its integration is a finite number. So the DCT now basically tells us, yes, you can evaluate this integration followed by a limit by actually doing the limit first. It's as if you are taking the limit inside the integral. Now, if you take the limit inside the integral, okay, then you have the limit of this function, okay, e to the I epsilon t. It's a continuous function, and basically the limit as epsilon goes to 0 is simply that you evaluate the function at epsilon equals 0. E to the power 0 is just 1, and so basically this limit will be 1, and you are left with this integral. Okay, so this limit here is exactly equal to the integral of eta of t itself, and the integral of eta of t is well defined. It's well defined because we have this theorem that if a function is absolute integrable, then it is integrable. And this is true for Riemann integrals and for Lebesgue integrals, okay? And so basically this integral here is a well-defined quantity, and it is equal to basically these two operations together, the integral involving eta of t e to the minus epsilon t, followed by taking the limit as epsilon goes to 0. Triangle inequality. Very important, very useful, used in lots of proofs, in systems, in probability, and so on. And you already know the case of two complex or real valued numbers that basically the magnitude of the sum is less than or equal to the sum of magnitudes. In fact, this is true even if you have an infinite number of complex numbers. Okay, so this is true even in the infinite case. So the triangle inequality, we have basically those numbers. Each one of them is complex. Okay, and if each one of them is complex, then we can write it as a magnitude and an angle or an argument that is from 0 to 2 pi. And basically the magnitude is, as I said on basically the previous slide, basically the magnitude of any complex quantity is square root of the square of the real part plus the square of the imaginary part. And just as a reminder that basically the magnitude of a complex number is 0 if and only if the number is 0. And the conjugate of a complex number, it has the same magnitude as a complex number, but basically its angle is minus. So if the complex number has an angle phi, then the conjugate will have an argument or angle that is minus phi. And if you want this 2 pi, you can just add 2 pi. Okay. And we know Euler's identities. Those are very important, very useful in signals and systems. So e to the I theta is cosine theta plus I sine theta. And cosine theta is e to the I theta plus e to the minus I theta over 2, and sine theta is e to the I theta minus e to the minus I theta over 2i. So basically those guys are very, very important in this course, okay? Now, suppose that you take the summation k from 1 to n zk, and you take the magnitude squared of this sum. Okay, so now we are trying to prove the triangle inequality. So suppose that you sum n of those guys, and after doing that, you take the magnitude square. So what is this summation here? What is the magnitude square of the sum? So this summation is like this. It's as if you are multiplying two brackets. Okay, so the magnitude square of a complex quantity is the quantity multiplied by its complex conjugate. So this is another way of basically talking about the magnitude square. So if you have the magnitude squared of complex quantity A, it is A multiplied by A conjugate. So if you have a bracket with Z1 up to Zn, and you take the magnitude squared, then you basically take Z1 plus Z2 plus Zn, and you multiply this by the complex conjugates up to Zn conjugate. Okay, so this will be the magnitude square. And so when basically you do the multiplication, you take each term in this first bracket and multiply it by by all other terms in the second bracket. And so the magnitude squared of the sum will be a double sum, k from 1 to n, m from 1 to n, zk, zm conjugate. Okay, so this is basically carrying out this product operation and representing it in this compact form as a double sum, because you take basically a number from the first bracket and multiplied by the conjugate of or from a number from the second bracket, which is the conjugate. It contains the conjugates. Okay, so now the trick is that you take this double sum and you divide it into two parts. So the first part, okay, so this double sum, it has n squared terms because each index has n values. And what you do is that you focus, basically the first part here is when the two indices are equal to one another. So if k is equal to m equal to 1, k is equal to m equal to 2, up to k equals m equals n, then you get this summation here. When the two indices are the same, you have zk multiplied by zk conjugate, and again you have a complex quantity multiplied by its conjugate. This is the magnitude square, and then you basically have the other terms. Okay, the other terms in the double sum. So in this case, the other terms will basically be different. So the indices will be different. Okay, and so we can write basically the remaining terms as this double sum here. Note that m goes from k plus 1. Okay, it's from k plus 1 because whenever m is equal to k, whenever the two indices are the same, we already took care of that in this summation here. Now take these complex numbers and write them in their polar form, which means take each complex number, write it as magnitude and an angle, and so you will get this result here, right? Because zk is equal to magnitude zk e to the phi k, and it's multiplied by zm conjugate. So zm conjugate is the same magnitude as zm, but you have a minus sign here, phi m, right? And similarly, we do it here. And so basically, you write down your complex numbers now in polar form. And then you find that you have this one is e to the I phi k minus phi m. And what is this? This is e to the minus I phi k minus phi m. So we have something that looks like this. So you have e to the I an angle plus e to the minus I multiplied by the angle. So basically the sum of these two exponentials will be double the cosine, right? Because the cosine is cosine theta is e to the I theta plus e to the minus I theta divided by 2. So e to the I theta plus e to the minus I theta will be double the cosine. So this is what we have here. We can combine these two terms and have a 2 and then have the cosine of the angle. And the angle here is basically the difference between the two angles. Okay? And now you have a cosine. And what the cosine function? The cosine function is less than or equal to 1. It is less than or equal to 1. And it is 1 if and only if basically we have a 0 here, or 0 plus plus basically the integer multiples of 2 pi. So if you take if we take the principal argument of each complex number, which is you define each angle from 0 to 2 pi, then basically this thing here will be 1 exactly when the argument is 0, when the two angles are equal. Okay, so how do we get the triangle inequality? So you get the triangle inequality by taking, again, you start with the sum of the complex numbers. You take, after doing the sum, you take the magnitude square. We have equality here, equality here, equality here, but now you can upper bound by saying that this cosine is less than or equal to 1. So you can basically say that we have an upper bound on this magnitude squared, which is the sum of the magnitude squares plus double the double sum, and then you replace the cosine by its upper bound. The cosine can never exceed 1, and so you replace this by 1. Okay? And now you can basically recombine all these terms as the summation of the magnitude of zk squared. All those guys, and so it's like the opposite step of what we did at the beginning here. You can recombine this sum and these, and basically this sum as the summation k from 1 to n of magnitude zk, now all squared. Okay, so let's write our result. So if we do the sum, so here we do the sum first, and then you take the magnitude squared. Now, what is this quantity versus that you sum the magnitudes. You sum the magnitudes and then square, like this. Because the cosine is less than or equal to 1, this quantity will always be less than or equal to this quantity. And both quantities on both sides are basically non-negative, and so you can take the square root and you get basically the triangle inequality. Okay, so the triangle inequality is this statement. It's very important. The sum of quantity, you take the magnitude, is less than or equal to the sum of magnitudes. This is always true, and I will not go into the details, but this is also true if the summation goes to infinity, and if basically the sum of the zk's makes sense when you take n basically as infinity. So this is true even for the infinite case. But what is also useful, and I want you to keep in mind, is not just the triangle inequality, which is sort of, if those are real numbers, the triangle inequality tells you that you take a bunch of real numbers, and if you sum them and then take the absolute value, you always get a result that is less than summing the absolute values. What can be important in some applications is when is this inequality satisfied with equality. So when is it the case that basically we have an equality here that is guaranteed? So let's go to the real numbers. So if you have a bunch of real numbers, you sum them and you take their absolute value versus summing the absolute values. When do you get equality? You think about it, and you get equality if all the numbers are positive, right? If all the numbers are positive, then summing the numbers, taking the absolute value, is equivalent to summing the absolute values. And it's also true if all the numbers are negative. If all the numbers are negative, you sum them and take the absolute value. It's equivalent to summing the absolute values. Now, what about the complex case? So this will be a generalization, and the trick here is to focus on what actually led us to put the inequality sign during when we did the derivation. It's basically this thing. We actually get the inequality. We get the inequality by upper bounding the cosine by 1, right? So basically we get equality if the cosine is equal to 1 always. And the cosine is equal to 1 always if all the complex numbers of interest, z1, z2, z3, and so on, all of them, they have the same argument, the same angle. So this is the condition of equality. So we have equality if and only if all the z's have the same angle. Okay, so keep this in mind. Now, if the z's are real numbers, then basically, a real number, its angle is either 0 if the real number is positive, or basically it is 180 or pi if the real number is negative. Okay, so basically that's the reason that for real numbers, the triangle inequality is satisfied with equality if all the numbers are positive, because all of them have the angle 0, or if all the numbers are negative, because in this case, basically all of them will have the angle pi or 180 degrees. Generally speaking, the triangle inequality will be satisfied with equality if and only if your complex guys, they have the exact same angle. And again, I will not go into details. You can read it, that basically this is true even if you have a collection, a countably infinite collection of complex numbers. Okay, so let me actually do something quickly. So it may be useful maybe in this course or some other course, which is basically the reverse triangle inequality. Okay, so reverse triangle inequality. Okay, so let's do it. This is for two numbers. Okay, two numbers. So suppose that you have absolute value of a, or the magnitude of a if a is so let's take two real numbers. Okay, so to make things easy, two real numbers. So the absolute value of a can be written as a, absolute value of a, minus b plus b, right? So I just have plus b minus b, right? So by the triangle inequality itself, this is less than or equal to absolute value of a minus b plus b, plus the absolute value of b, because the triangle inequality tells you that if you take two quantities, here one of them is a minus b and the other is b, if you sum and then take the absolute value, you get something that is always less than or equal to the absolute value of the first guy plus the absolute value of the second guy. Now move this to the other side. So basically we have absolute value of a minus b will be greater than or equal to absolute a minus absolute b. Now you can do the same trick with the absolute value of b. The absolute value of b can be written as the absolute value of b minus a plus a. This is an equality. Now, again, think of this as one quantity, and this is your second quantity. This is your first quantity. This is your second quantity. Apply the triangle inequality. So this is less than or equal to the absolute value of b minus a plus the absolute value of a. Now, the absolute value of b minus a, this is, changing, basically the order inside the absolute value is the same. So this is equal to absolute value of a minus b. And again, move this term to the other side, you'll get this absolute value of a minus b is greater than or equal to the absolute value of b minus the absolute value of a. So basically, this is called the reverse triangle inequality. So the triangle inequality, you have an upper bound on the absolute value. The reverse triangle inequality is that you have a lower bound. You have a lower bound on the absolute value of the difference of two quantities. And sometimes it's very useful, and actually you can combine these two guys, right? Because if you know that absolute a minus b is greater than or equal to this, and it is greater than or equal to that, so basically the difference between these two guys is that the order is reversed. So we know that the absolute of a minus b is greater than or equal to the absolute value of absolute a minus absolute b. Okay, so again, keep it in mind, the reverse triangle inequality, sometimes it's a lifesaver and it's used in derivations and to obtain useful results. The triangle inequality is applicable to integrals. Okay, so this is very important, that basically whether they are Riemann integrals or Lebesgue integrals, basically if you evaluate an integral, then you take the absolute value or the magnitude if the function is complex valued. This will always give you a result that is less than or equal to basically the integral of the magnitude itself. Okay, and you know, this is not a rigorous proof, but like inspired by our proof for sequences, we have equality if and only if x of t has the same angle almost everywhere. Okay, so this is again an important thing, and it's very useful in basically this course. So the concept of a norm is a concept that, you know, is important in signal processing. Typically, we are interested in norms and in inner products. So a norm is a general concept that is applicable to you know, to a vector space. So you should have a vector space with a field, and in this course, we will typically use the complex numbers as our field. Okay. And so the norm is a function that is applied to the vectors of a vector space. And it's not an arbitrary function. It must basically satisfy a bunch of properties. So basically, when you apply the norm to a vector from the vector space, it should give you something that is real valued and non-negative. The norm is exactly equal to 0 if and only if we are talking about the 0 vector of the vector space. The norm applied to a vector multiplied by scalar from the field of the vector space should give you the norm of the vector multiplied by the magnitude of the scalar. And finally, we have the triangle inequality. Now, it's this version of the triangle inequality is the triangle inequality for vectors, which means that the norm of the sum of two vectors should be less than or equal to basically the sum of the L2 norm of the first vector plus the second vector. So basically, that any norm should set it. It's not a norm unless it satisfies the triangle inequality for vectors now. So you take two vectors, you apply the norm to them, you should get a result that is less than or equal to the sum of the norms. Now there are so many norms. You can define anything again that satisfies these three properties will be a valid norm. There are so many norms. For our course here, we will be interested in the LB norms. Okay, the LB norm of a vector, and so this is a vector in the n-dimensional complex space. So it's basically a vector, it's an n-tuple of complex numbers. And basically the LB norm is defined by this quantity here. So you take the components of the vector, so you take x of 0, x of 1, x of 2 up to x of n minus 1, you take the magnitude of each component. So each component is a complex number. So you take the magnitude of each component. Okay, then you do what? Then you raise the magnitude to the power p. You raise the magnitude to the power p. Then you sum. You sum those guys. Then after summing, you take the bth root. It's as if you raise the sum to the power 1 over p. So when you compute this quantity, you are computing something called the L, and here it's a small l, the LP norm of a vector in the n-dimensional complex space. Okay, so the L2 norm, you know, we will take it for granted. You can show actually that something defined as such will satisfy the three properties of the norm. So perhaps you already know this from a course on linear algebra or something, but here we'll take it for granted that this function is indeed a norm. Okay, it is a valid norm on the n-dimensional complex space. Again, you take each component in the vector. Generally, it's a complex number. You take the magnitude of each component. You raise the magnitude of each component to the power p. Then you sum, and after summing, you raise basically the sum to the power 1 over p, which means that you compute the bth root, and B is any real number that is greater than or equal to 1. So B is not necessarily an integer, okay? So B is a real number. So generally, it's a real number. Okay, you do not have to. Yes. What's the question?
This also applies if the numbers are not complex, right? Because
What?
take for example the L2 norm of not like
Yeah.
of real vectors, it's going to be the square root of the square of the elements.
Yes, so basically if your vector is of real numbers, then basically the magnitude corresponds to the absolute value. So basically you take the absolute value and you raise to the power p. Note that the L2 norm you are squaring. Squaring is equivalent to taking the absolute value and then raising to the power 2. Okay, so basically the two like very important norms. So we have the L1 norm. So what will be the L1 norm? So the L1 norm is equal to 1.
Will be the sum, right?
In some of the absolute values or the magnitudes. So basically in this course we will be interested in B equals 1 and B equals 2. So B equals 1 is called the L1 norm, and the L1 norm of a vector X is basically the sum of the magnitudes or the absolute values if our stuff is real valued, n, okay, or n minus, let me stick to the same notation, x of 0, x of 1, and here x of n minus 1. Again, you take the magnitude or the absolute value, you raise it to the power 1, and then you raise the sum to the power 1 over 1, which is 1. So it's just the sum of the absolute values or magnitudes. This will be the L1 norm, okay, very important. And for the L2 norm, okay, of a vector, what you will do is that you will take x of 0 squared, x of 1 squared, and so on. You sum, and then you raise to the power 1 over 2, which means that you take the square root. Okay, so the important guys are the L1 norm and the L2 norm. There is also an important norm, which is the L infinity norm. And the L infinity norm is sort of like you take it from here by taking the limit as B goes to infinity. And, you know, again, we'll just take its final form. It is basically obtained as such. For the L infinity norm of a vector, you compute the magnitude of each component in the vector, which is the absolute value if the components are real valued, and then you hunt for the maximum guy. Okay, so basically the L infinity norm, it's the maximum magnitude. You simply compute the magnitude of each component, each basically element in the vector, and basically the maximum of those magnitudes is the so-called L infinity norm. Okay, so three very important norms in signal processing, basically the L1 norm, the L2 norm, and the L infinity norm. Now the norms can be extended, those norms can be extended to the cases of infinite dimensional vectors. So if the components are basically of those vectors, you know, go to infinity, if there is a countably infinite number of elements in each vector, you can still extend the definition of the LP norm so long as the sums, now the sum will be an infinite sum so long as the sum is a finite number. Okay, so for a discrete time signal, so this is a discrete time signal, so it is x of 0, x of 1, x of 2, and it never ends. So you can think of it as an infinite dimensional vector of complex numbers. You can still define the LP norm same way. So you will take the magnitude of each guy, then you raise it to the power p, then you sum. Now you have a problem because sometimes this summation will not be finite. This is not the case if you have a finite number of finite terms. Now, each term may be finite, but the sum may explode to plus infinity. So basically, if if the summation is finite, we are fine, and basically you are not done yet with the norm. You will need to raise it to the power 1 over p. And in the case of the L infinity norm, you will have basically to compute the supremum rather than the maximum, because the maximum may not exist. Okay, so the L infinity norm, if you want to define it rigorously for an infinite dimensional vector, something like a discrete time signal defined over the non-negative integers, then you will have to use supremum. So imagine that your vector is something like this. So imagine that your vector is 0, okay? Let's say that it is 0, then it is 1, then it is 1 minus 1 over 2, 1 minus 1 over 3, 1 minus 1 over 4, 1 minus 1 over 5, and so on. Okay? So what is okay, no, I don't know, I want this to be 1. Okay, so I will put this equal to also 0. Okay, so suppose it's, it's, okay, let's assume that the first element is 0, and then the other elements are 1 minus half, 1 minus third, 1 minus 1/4, 1 minus 1/5, and so on. Okay, so this is my x of 0, x of 1, x of 2, and so on. So what is the L infinity norm again? You take the magnitude of each guy. Okay, so those are non-negative numbers. So their magnitude is basically themselves. Then you hunt for the maximum. But what is the maximum? What is the maximum of those guys? So basically, 1 minus exactly, each element, so you have a 0, and then you have 1 minus a number. 1 minus a number that can be made ridiculously small, right? But for every positive integer, this number, which is 1 minus 1 over n, this is strictly less than 1 for every n that is a natural number. So you never reach 1. But you get close to 1, okay? So you need to define basically things using the supremum and not the maximum, okay? And basically the L infinity norm of this vector here, it is 1, okay? It is 1, but we do not say that it's a maximum because the maximum is not an element in the vector. There is no element here that is equal to 1, but you can get close enough, okay? So basically, so we have norms. The LB norm is very important, specifically L1 norm, L2 norm, and L infinity norm. And basically, those can be extended to the infinite dimensional case. Okay. And so basically, the L1 sequences or discrete time signal, let's write it explicitly, L1 sequences or discrete time signals, they are signals for which the L1 norm is strictly finite. It's a finite number, okay? So we say about a discrete time signal that it is L1. It's an L1 sequence. If basically you try to compute its L1 norm, which is the sum of magnitudes as we have defined it, and you find that you get a finite result. So in that case, your signal is called L1, or you can say that it is absolute summable. Absolute summable, which means that taking the magnitude and then summing the magnitudes will yield a finite number. Now, a discrete time signal is called L2, or square summable, if you basically take the magnitude square of each element or each component, then sum those guys, take the square root, you get a finite number. Okay, of course, if this is finite, okay, so this is finite if and only if the sum itself without the square root is finite. So what about L infinity sequences? So what is the L infinity norm again? The L infinity norm, you take the magnitude of each component and then you hunt for the biggest guy, hunt for the maximum in the finite case or for the supremum in the infinite case. So for the L infinity norm to be finite, it means actually that your sequence is a bounded sequence. So L infinity discrete time signals are signals that are bounded. So bounded means that for every n in 0, 1, 2, and 3, the magnitude of x of n is less than some number m, which is strictly finite. Okay, so those are the L1, L2, and L infinity norms and sequences. Sequences, again, is typically the word used in the math literature, and this is exactly what we in signals and systems call a discrete time signal. Okay. If we talk about functions, okay, if we talk about functions, you know, we can also define LB norms, but now L is written as a capital L, okay, and L of course is, you know, L is the letter of Lebesgue. Okay, so this L business is the, you know, the first letter in Lebesgue, you know, the mathematician who basically invented the Lebesgue integral, and who basically did significant contributions to measure theory. Okay, so for continuous time signals, we can define norms. Okay, so we can define LB norms, and now the LB norm, of course, it depends on basically the domain of your integration. So sometimes we integrate over basically a closed interval, let's say from 0 to 1, or from 0 to some finite number. Sometimes we integrate from 0 to infinity. Sometimes we integrate from minus infinity to infinity. So again, we will basically see the cases later. But the norm is computed like for vectors. But so now you take x of t, you take its magnitude, then you raise it to the power p, right? And then, because this is now a function, then you integrate. So the difference is that for vectors or sequences, we do a summation. Now we will do an integration, and of course we need to specify the domain of integration. Again, typically we will integrate from 0 to some finite number, 0 to infinity, and so forth. And we are not done yet. We need to take the bth root. So we raise this thing here to the power 1 over p. And if we talk about the L infinity norm, then basically we take the supremum of magnitude of x of. Okay, so S here can be the full set of real numbers, which means that those integrals are from minus infinity to infinity, or they can be from some finite a to some finite b, and so on and so forth. Now we have, you know, our continuous time signals. Can, you know, the important ones that we use are L1, big L1, and big L2. So L1, those are the absolute integrable functions or continuous time signals. So those are the signals that if you take their magnitude and you integrate, let's say from minus infinity to infinity, then you get a finite number. L2 signals will be signals that are called square integrable. And the reason for that, if you take the magnitude square and then integrate, then you get a finite number. So of course, this is true if and only if the integral itself is true. But not something that the definition of the norm requires that you should take the square root. You must take the, so if I tell you compute the L2 norm of this continuous time signal or of this function, then you need to take the magnitude square, integrate it, and then take the square root, because it's in the definition of the norm. Okay, but of course, checking whether this thing is finite, you can just check the integral itself, and the integral itself, it has a name. And what is the name? So this is what the integral of the magnitude square. It's the energy. So this is what we'll later call the energy of the continuous time signal. So basically, the energy is simply the square of the L2 norm. Okay, so now this is like, you know, a repetition of what what we say that for basically, it's a subtlety. There is, okay, so yeah, let me say it actually. It's a subtle point, but won't harm if we know it. Okay, so in the definition of a norm, so if you go to a course on linear algebra and see what are the properties of a norm, so we have the first property is that the norm of a vector, okay, so if you choose any vector and any general norm, to be a norm, the norm of a vector should be non-negative and it should be 0, so it can be 0. It's 0 if and only if we are talking about the 0 vector, right? So for the norms for sequences, so if you have a vector like x0, x1, and x, it goes, let's assume that it's infinite. So the LB norm is 0 if and only if our vector is basically the all 0 vector. It's 0 everywhere. And this is true and not problematic. This is true and not problematic, okay? But now I talked about those big L norms, and I said, for example, that the L1 norm is basically the integral of the magnitude. Okay, so now here is the question. If you have the integral of the magnitude is equal to 0, if the integral of the magnitude is equal to 0, what does this mean regarding x of t? You will 0 function, great, but is it the only solution? Is it the only solution? So at the beginning of this lecture, remember, almost everywhere, if you have a function that differs from 0, almost everywhere, that differs from 0 on a set of measure 0, right? So suppose that you have a function y of t that is equal to 0 almost everywhere. Now this function may be non-zero, on any set of measure 0. So it may be non-zero at a single point or at a finite number of points, or it can be non-zero at all rational numbers, because rational numbers are countably infinite, and so they constitute a set of measure 0. A function that is 0 almost everywhere, the integral of its magnitude is equal to 0 because of this property I talked about at the beginning of the lecture, that integrals are blind to differences on sets of measure 0. Give me a function. If you take this function and integrate it and you get a number, now take the same function and change its values on a set of measure 0. Let's say you change the values of the functions at all rational numbers. Guess what? The integral is exactly the same as before, because integrals are insensitive to differences on a set of measure 0. So basically, if the L1 norm is 0, maybe in your previous life you will say that x of t is equal to 0. Now you should say that this implies that x of t is equal to 0 almost everywhere. You must say it now like this. X of t is 0 almost everywhere. Okay? So now here is something. According to the rules of a norm, a norm should be equal to 0 if and only if we are talking about the 0 vector. So for functions, what is a 0 vector? So the 0 vector is not just the all 0 function. It's every function that is equal to 0 almost everywhere. Okay, and so we have actually a huge number of functions that are like this. For practical purposes, those functions are like 0, but they can be like very scary. For example, this function I talked about at the beginning of the lecture, the function that is equal to 1 at all rational numbers. This function is indeed equal to 0 almost everywhere. Because it deviates from 0, it is equal to 1 only on the set of rational numbers. The set of rational numbers is a big set, okay? It's dense, rational numbers are everywhere on the real axis. However, they have a measure 0. Okay, so now our zero vector for vectors or sequences is the all 0 sequence, but for functions it is something that is 0 almost everywhere. Okay, so this is some technical point that we need to pay attention. The difference between functions, continuous time signals, and sequences, which are like discrete time signals. Two very important inequalities. Basically, they are very useful, and they come with probabilistic versions. So they are also used in probability, but of course here we will focus on the deterministic versions. So the Holder inequality, and then it has a special case called the Cauchy-Schwarz inequality. Okay, so what is basically the Holder inequality? So let me actually give you the statement before doing the proof. Okay, so the Holder inequality tells you that if you have two vectors, so x and y, so you have two vectors x and y, and it's applicable to the infinite case, but I mean just focus on the finite case. So this is a vector x of 0 to x of n minus 1, and this is y of 0, y of n minus 1. So each vector is living in the n-dimensional complex space. Now you can form something called the inner product of these two vectors. And so what is the inner product? The inner product of two vectors, okay, is defined as x Hermitian y. So this is called the inner product, x Hermitian y, and it is this summation I will write here, which is summation j from 0 to big N minus 1 x conjugate of j, y of j. So what you do basically in this inner product, you take the conjugate of this guy times this guy, plus the conjugate of x of 1 multiplied by y of 1, and so on and so forth. So this is called the inner product. And for functions, basically the inner product of x of t and y of t is the integral over a domain that is of interest in some problem, maybe from 0 to infinity, the integral of x conjugate of t, y of t dt. Okay, and we use these things in the basically Fourier analysis. For now, I mean, you can just focus on the integral, or in our case here, the summation. So we have this quantity here. So x Hermitian y is this quantity. So you can find an upper bound on the magnitude. So this is the magnitude of y Hermitian x. So y Hermitian x, this will be this summation here. So basically, because we have y Hermitian x rather than x Hermitian y, the conjugate now is with the y, not with the x. You can upper bound this summation here, or the magnitude of this summation here, by a product of the LB norm of vector x and the LQ norm of vector y. B and Q are not arbitrary. B and Q are not arbitrary. B is any real number between 1 to infinity, and the Q is related to B with this relationship. 1 over P plus 1 over Q is equal to 1. So basically, magnitude Y Hermitian X is upper bounded by ubiquity B between 1 and infinity. 1 over P plus 1 over Q is equal to 1, which means that if you have B, 1 over Q is 1 minus 1 over B. The magnitude is upper bounded by the LP norm of vector X multiplied by the LQ norm of vector Y. Okay, so basically, if we write this explicitly, what is the LP norm of vector X? You take the components of vector X, the magnitudes, you raise them to the power P, you sum, and then you raise to the power 1 over P, and the LQ norm of vector Y, you sum, let's do it in the order. So you take the magnitude of each component in Y, you raise it to the power Q now, Q, you sum, and then you raise the result to the power 1 over Q. So again, you can upper bound by the product of these two norms, the LP norm of vector X, the LQ norm of vector Y, so long as, again, you obey those guys here. You choose B to be greater than or equal to 1, and you may choose B to be equal to infinity. Once you fix B, then basically Q is specified. Q and B are related with the relation 1 over P plus 1 over Q is exactly equal to 1. So if you choose B equals infinity, 1 over infinity is 0, and so Q will be 1. If you choose B, so B infinity, then you need to choose Q equals 1. So what if you choose B to be equal to 2? If you choose B to be equal to 2, then 1 over 2 plus 1 over Q is equal to 1, right? So from this, we have 1 over Q is 1 minus 1 half. Move this half to the other side. So 1 over Q is 1 half. So Q is also equal to 2. Right? So if you choose P to be equal to 2, then Q is 2. And this is the special case that is called the Cauchy-Schwarz inequality. Okay, so the Cauchy-Schwarz inequality is the special case of the Holder inequality, in which basically you fix P at 2 and Q will be equal to 2. But you do not need to do this. For P, you can choose any number from 1 to infinity, and you compute Q using that 1 over Q is 1 minus 1 over P. Okay, so next time what we will do is that we will prove Holder's inequality. Okay, and basically the proof relies on this result here called Young's inequality. So Young's inequality is this result if alpha and beta are positive numbers. So basically alpha and beta are positive numbers. Okay, you can show, and I will leave this to you, it is straightforward. And actually you can I mean, if you know concave and convex functions, you can basically use the concavity of the logarithmic function to show the Young's inequality very easily. But if you don't know it, you can basically use standard calculus to show that if you have two positive numbers, alpha and beta, and if lambda is a number living between 0 and 1, then basically alpha to the power lambda, beta to the power 1 minus lambda is upper bounded by lambda alpha plus 1 minus lambda beta.